Hey guys, and welcome to a new video. In this video here, we're going to implement the DETR transform model for object detection in a custom Python script. So we're basically just going to open up a Python script from scratch, and then we're going to show you how we can implement this object detection model from Ultralytics. So we can basically just import it from Ultralytics. We're going to create a class around it so we can extract all the information, all the results that we get back from the model. And then we're going to see that we can actually use transformers for real-time object detection. So this model here is called real-time DETR. So this is a vision-based transformer. So I'm really excited to see the results here. We're going to implement the whole class from scratch. Let's see how fast we can do it, and let's just jump into it and get started. So we're now jumping into Visual Studio Code, and we've created this empty Python script that we're going to use, and then we're basically just going to implement the whole class from scratch, import the model, see how we can use the results and so on, and also how we can visualize the results later on. So let's just start with actually importing the different modules that we need. So we need PyTorch to run our model, and also we have a GPU available. So I have a 4090 graphics card from NVIDIA on this computer here that we're going to run it on, so it will actually be able to run in real time. Again, this is really nice because now we can actually go in and use transformers for object detection as well. Now we don't really need these CNN-based models like the YOLO model, for example. So I also have videos about the YOLO models, both YOLO v5, YOLO v6, 7, 8 here on the channel, and also the new YOLO NAS model. So those are some pretty cool models, but now we also see some pretty good results with the vision-based transformers. So transformers are actually performing really, really good on object detection and just computer vision tasks in general. So let's just import the different modules. We also need NumPy. So we're just going to import that as NP, and then we also need to import CV2. And then here from time, we're also just going to import time, so we can time how long it actually takes to run through our images and pass our images through the script, and how fast we can do inference. So I think we're going to get around 20-30 frames per second, and then we're actually able to run these VIT models in real time. So then we also need from Ultralytics, we actually just need to import the model. So again, here we're just going from ultralytics.vit. So to have this module from Ultralytics called VIT, and then we can import the real-time DETR model. Then we also need supervision from RoboFlow, so we can actually go in and visualize the results easily. We're also going to go in and extract them. I have videos about that here on the channel, how we can use supervision and all those different things. And we also have the other models for YOLO v8, where we basically just extract the results, visualize them with supervision. But in this video, we're going to implement a class where we extract all the information, all the results from the model. So after I pass an image through our model, we'll get the results, so we can use those results in our own applications. It could be stored to a file, do different operations on it. It could be, for example, only detect a certain class, or if you're doing custom object detection and you want to do something with the results afterwards. So here we're going to import supervision as CV. So now we have that for the visualization. So now we have all the modules needed imported already, and then we can go down and create our class. So we're just going to call that DETR class. So when we're going to implement the code here, I'm going to use GitHub Copilot to actually just auto-complete these lines that I'm going to write, because this is basically just set up for standard classes as well when we're setting up these models. First of all, we'll need an initialization method here. So we just call our def init. Here we're just going to create an instance. So here we have self, and then we also need to have the capture index. So we're going to run this on a webcam in real time. So we give our class here the capture index of our webcam that we want to run real time inference on. So now we have the initialization method here. So now we can basically just go down and set self.capture index. So we're going to set that equal to our capture index, so we can use that later on. Then we're also going to set the self for the device. So we're actually going to use CUDA here if it's available. If it's not, we're basically just going to use the CPU. So that depends on your computer or the desktop or laptop that you're using. So I have a CUDA GPU available, so it's going to use that. We basically just store that in this variable self.device. I'm just going to zoom out here a bit so you guys can see what's going on. Here I'm just going to print out what we're actually doing. So here we're just going to print using device, and then we just print the device that we're using, just to make sure that we're actually seeing what we're using, CUDA or the CPU. So when you create an instance of our class, we're basically just going to print that out. So let's now go down and actually just initialize the model. So we just have self.model. We set that equal to the DETR from Ultralytics. So again, we can basically just call that method. So we have the RT-DETR, and then we can just specify like the parameters for that. So we have RT-DETR, and then they have different kind of like models for that. So they have different sizes of those models. In this video here, we're just going to use the large model. They also have some other ones like small and medium. You can go in and find that in the documentation. We can probably like test out a bunch of them, but here we're just going to run the large model. I will also be able to run that because I'm using a 4090 GPU. So now we need to go in and actually get the class names of our model. So again, this model here is trained on a Cocoa dataset. So we're going to extract those classes. Again, we're just using these pre-trained models. You can also fine tune them on your own custom dataset. And this is the exact same thing as in all the other videos with YOLO V8, YOLO NAS, and so on. You can basically just create another instance of the model. You can just swap out the model here for your own application or like a specific model that you're using. And then you can use the whole class structure here in your own project and application if you're using other models as well. So here we're basically just going to have self.class names, and we're just going to type that out. So class names underscore dict. We're going to set that equal to self.model, and then inside our model we can basically just extract the model, and then we can directly get the names of the classes that our model has been trained on. So now first of all, we're just going to print them just to make sure that we actually have the classes so we can extract them later on for visualization. We can also go in and map them to the actual classes in the Cocoa dataset. We can go in and filter our results based on if you only want to detect a specific class. Let's say we only want to detect persons in our image, then we can go in and extract those values and basically just filter out the results. So now we're going to set up our box annotator from Supervision so we can basically just visualize the results later on when we have passed our image through the model. So we're going to set up our box annotator. We have cv.box annotator. We're going to set up like the color palette, which is the default one. So basically just the colors for that. So cv, and then we have something called the color palette, I think. Yes, there we go. And then we're just going to use the default one from Supervision. So now we have that, we can specify the thickness. We're basically just going to set the thickness equal to 3. We also have the text thickness. So again, you can play around with these depending on your application and so on. Again, we're just going to set that equal to 3. And then we also have the text scale. There we go. We're going to set that equal to 1.5. So now we should actually have all the parameters necessary for setting up this box annotator, and then we can draw bounding boxes around our objects detected later on. So this is basically everything that we need inside of our initialization function or our constructor when we're creating an instance of our class. We just take in the video capture index, and then we can use that later on to open up a video capture with OpenCV. Specify the device we're going to use. We initialize the model. We also get the class names for our models or like the classes that our model has been trained on. Could either be like pre-trained model or if you have fine-tuned a model on a custom dataset, and then we set up our box annotator for visualization purposes. So now we can basically just go down here and create a function for actually like plotting the bounding boxes and extracting all the results that we get after passing like an image through our model. So we're basically just going to call that like plot boxes. We could also call it like process results or something like that. But here I'm just going to call it plot boxes. So bounding boxes. It takes in an argument. So let's just delete this one here, and it takes in self. And it also takes in the results and also the frame that we're going to actually like visualize and draw the results on, or the bounding boxes. So let's now go down and write the actual like code. So I'm just going to write a comment here. So now we want to extract the results from our actual like model. So we're basically just going to extract the results. There we go. We can go in and take the boxes directly. So here we're basically just going to return the results. This is not the correct format that it is actually like suggesting right now. So right now we go inside the results. We just take the 0th index of that. And then inside of that, we have an attribute called boxes. So this is how we can get the bounding boxes inside the results. So this is basically just like a class or like the structure that Ultralytics is using for the results that is returned by the predict method on the model. So when we take a frame, pass it through the model, we get our results back, and then they have actually just created a class containing all these different kind of like attributes. So after boxes, we're going to convert that to CPU because we're going to use nump or like the GPU. So we need to like convert it back to the CPU again before we can process it with NumPy and so on. So now we have the boxes. We can also get the class ID. So here we have class ID is equal to boxes dot CLS. So this is how we get the class ID. Again, these boxes here are already on the CPU, so we can just directly extract the class ID. We can also get the confidence score. So the confidence score is equal to boxes.conf. And we can also get the XY here, which is the boxes.xy. And this is how we can extract the coordinates of our bounding boxes. So the top left corner and the bottom right corner of our box. So now, first of all, we need to convert our class ID so they would actually like be floating point numbers when we're going to use it, when we're actually like going to map it back and forth, and when we're going to throw it into supervision, we actually like need to convert that to integers first of all. So let's just do that to start with, just to make it easy. So we're going to set the class IDs equal to the class IDs as type, as underscore type. And then we're basically just going to set it equal to, let's do NumPy instead here, so np.integer 32-bit. So again, we're basically just converting from floating point numbers to integers, so we can work with them later on for visualization purposes, but also we don't really need floating point values when we're doing mapping back and forth between like indexes or values and act like class attributes that we have trained the model on. So now we can set up the detections for supervision. So now I have extracted all the results here. You can actually like just go in, return these results here, or you can go in and append them to list. So if you actually want to detect like multiple objects over a number of frames, or like you just want to get like all the objects that you're detecting for each frame, you can store that on list in the class as well. But this is basically just how you can extract all the information. So these will be like all the bounding boxes, all the class IDs, confidence scores, and the bounding boxes down here for all the detections in a single frame returned in this results variable. So we're going to see how we can actually like do a forward pass of our image in just a second, but here we're just creating this function for plotting our bounding boxes. So now we're going to set up our detections. We're going to set that equal to CV. So we're going to use supervision for that. We set up our detections, and inside of that, we need to specify some parameters. So first of all, we need to specify the XY coordinate. We also need to specify the class ID, and we also need to specify the confidence score here. So I think they actually call it confidence like this. And then we have the class ID. So again, we basically just pass in the XY of our bounding box, the class ID that we want to draw as well, and also the confidence score. So this is how we draw the detections with supervision. So we don't really need to like go in and draw rectangles, put text on top of our rectangles and so on, and take care of the placement of our class ID and confidence score and so on. So this is really easy to use. So now we're going to go down and actually like extract the labels from our detections. So here we can basically just go in and create an if string. So we're going to set that equal to a list, and then we're going to create an if string. And inside of that if string here, we're going to have like curly brackets. We're going to take the class names dictionary, and inside of that one, we're going to have the class IDs. So we have class ID, and then we also need to change this I here in the for loop to class ID. Let's just make sure here we also have the confidence score. So here, let's just call it conf instead, or like confidence instead of just C. And we're going to change it over here as well. So confidence. And this is basically like what we need to do. But over here to the right, we can see that, okay, first of all, we extract the class ID here in the class names dictionary that we created up at the top. Then we also have the confidence score. We're basically just like only taking like 2 floating point values inside of our for loop here. I'm just going to scroll up a bit so you guys can see what's going on. So here, again, the class ID, confidence score, and then we just have a for loop like extracting all the information. We're zipping both the detections and so on here, but we don't really need to do that because we have already like everything inside of our detections, so we don't need to zip it. So it will basically just be inside of our detections from supervision. And again, this is returning both the XY. It's returning the mask. So if we're, for example, like using mask for instant segmentation and so on, we're not going to use that in this example here. Here, we're only doing object detection. So we have the XY, we have the mask, and we have the confidence score. So this is the third one that we're returning. So we just need to do a bit of restructuring here. And then the last one here is the track ID, but we're not going to use that. We can also use like trackers with supervision. So we're only interested in the confidence and also the class ID. So now we should have everything here. And now we're actually like just ready to go down and return the frame, or like to actually like draw the bounding box on top of our frame before we're returning it. So here we set frame equal to self.box annotator. We throw in the frame, we throw in the detections, and then we also throw in the labels that we want to draw on top of our detections. So again, all of these things here, we could do it ourselves. We can basically just call the rectangle function, put text, and all those stuff functionalities from OpenCV. But with supervision here, it's really easy to use. We don't really care about that much about visualizations. We just want to extract the results. And again, all the results here are extracted in these variables. You can like write them out to CSV files. You can like return them from this method if you want to use them in some other functions as well. Or you can basically just like append them to some other list, like some global list that you can use later on. So again, you will basically just need to use these ones. So now we have the frame. We have actually like just visualized all the detections on the frame, and now we can just go in and return it. So now we have this plot boxes function extracting the results and converting the class IDs to integers. We just extract all the information that we need to visualize the results. We draw the results, and then we return the frame where we have like visualized the results. So now we have that. Now we can basically just go down and create our call method where we're going to open up a video capture with OpenCV. So this will basically be our while loop running as long as the webcam is open. And then we're going to take the frame, pass it through the model, plot the results, and then we're going to run this real-time DETR model. So let's not just set up our function here or like our call method here for our class. So here we have call. Let's just delete all these arguments here. We don't really care about that. It basically just auto-filled that. So we have self, that is the only parameter that we're going to throw into our call method, because when we're initializing this class, we're already giving it the video capture or like the index of our camera. So now we're going to set up a video capture. We have the capture equal to CV2 video capture. We're going to take self.capture index. So now we have that. We can just go in and assert that this capture is actually like open. And if it's not open, it will just throw out a F string here that we failed to open the camera. We don't really need to do that. We know that, okay, if nothing is happening, we're basically just terminating our program if we're not able to open up our webcam. So first of all here, we're just going to set like the image width and also the image height. So this is how we can specify the resolution of our camera. So we're just going to do that to start with, because if you don't do this, OpenCV will just open up your video capture with 640 by 480, so it's a really low resolution, especially if you want like high resolution or you just want to like see the results better. Of course, it will run slower when you're using like large images, but it will also like downsize the image before throwing it through the model. So now we can basically just go in here. As long as the capture is open, we don't really need to like assert that it's open, but it's good coding practice to do that, especially before we're setting the width and the height of the camera, because we can't really do that if it's not open. We can either have like while the capture is open or just while true, but let's just have while the capture is open here. So now we can just go down and create a timer. So our start time, time.time. I prefer to use the perf counter. So this is a more accurate counter. So here we basically just have our start time. We're going to have return value. We have the frame, and then we're going to call cap.read. So we're reading in a frame from our webcam that we're going to pass through a model. So that is what we're going to do now. We have the results, and these are the results that we're going to pass through our model. So we have the results equal to self.model, and then this model function here from Ultralytics, it has a method called predict. So we're going to call this predict function or method. We throw in the frame, we get the results back, and then we can take these results and throw into the function that we just created up a couple of seconds ago. So now we're basically just going to plot the boxes. So we have our frame equal to self.plot boxes. We throw in the results and also the frame that we want to visualize the results on. Now we can go down and end our timer, because now we have basically done like a forward pass. We've done all the processing to our image and also the results that we're getting back from the model. So now we can end the timer and see how many frames per second that we get when we're using this real-time DETR model. So that we can basically just take 1 over end time, subtracted by the starting time. So this is how you can calculate the frames per second. And then we're just going to put that text out onto our frame when we are visualizing it. So we both see the detections, we see the frame, but we also see the number of frames per second in the top left corner. So we have cv2.putText. Here just auto suggest this one here. Let's just verify that this is correct. So I actually prefer this a bit lower. So let's just say 20 and around 70. BGR, so here we have the red one. Prefer to have the green one as well. So BG, so this is 255 and a 0 here, and the rest should be fine. So we're basically just cutting off like, so only have like 2 floating point values, frames per second. We put out that text, so that should be correct. So now we actually just have our frames per second. Now we can go down and visualize our frame with imshow from OpenCV. So here cv2.imshow, we have the DETR, the frame, and then we're going to show the results and see the results on this frame. So this is actually like everything that we need. We can just go down and create our if statement. So if we hit Q on our keyboard, we will break off the while loop and terminate our program. So if we're doing that, we will basically just go down, release our webcam, and we will also destroy all the windows that we have opened up with OpenCV. So now we should actually have the whole class here implemented. This is everything that we need. We have around like 80 lines of code to set up this class. So this is actually like a really simple class. We set up the class, take a video capture index. We check if we're using like CUDA or CPU. We initialize the model. We create like the functions for plotting the boxes, extracting the results, and then we open up our video capture, have a while loop running, taking our image from a webcam, throwing it through the model, get the results, process the results, and then we visualize the results. And then you can do like whatever you want to do with the results on your own for your own application and project. So last one here, we have the whole class here. You can either just import it into another Python script, or you can just go down here and create an instance of the detection. Here we're going to have a detector, transformer detector. Let's call it transformer detector because we are normally used to CNN-based models, like the YOLO model. So here we have transformer detector, DETR class, and then we're going to specify like the video capture index here. So I'm just going to set that equal to 0 in this example here. If you have multiple cameras, you might need to have like another index here instead of 0. And then we can call the transformer detector function. So this will be our call method that we just implemented with this while loop from OpenCV. So now we should act like have everything. Now we're ready to run the program and see the results from this real-time DETR model. So here we're just going to run the program up here in the top right corner. First of all, it's going to just initialize the model. Here we can see the classes that we're using. So we have 80 classes from the Coco dataset. We're initializing the model with the GPU. So now we can see we have this window up open. It is in HD. We can also see the results down here at the bottom. So this is basically just when we're calling the predict function from Ultralytics. We can see like how many milliseconds it takes for inference. So it's around like 30 milliseconds inference time, 30, 40. And then here we can see that it corresponds to around 18 to 20 frames per second. Again, I'm running this on a 4090 GPU from NVIDIA. So this is a pretty good GPU. So you might not get this performance here on your computer, but again, you can use the smaller versions of the DETR models. Again, I'm using the largest one here. So I'm using the real-time DETR large model. So now take the webcam up here and actually like see the results. I'm just going to take it up, and then we can actually like just see the results. So we can see we have all these classes here. We have the class index, we have the confidence score, and then we also have the bounding box around the objects that we're detecting. So in the Coco dataset, the 0th index here, or like the 0th class, is a person. So we can see that that is a correct prediction. We can also just like take it around here. We can see that we have my monitors. We have some mouses here. We have some keyboards. It's also like detecting that fairly nice. So again, we can see it runs pretty fast here. We get around like 18 frames per second on average. If we're moving it around, it is actually like pretty responsive. You can even like, if I take it over here, it actually like even detects me here in OBS, which I'm recording on. So this is actually like a pretty good model. We get some really nice results. And that is also the case with these transformer based object detection models. The transformers are actually like really good for computer vision tasks as well, and not only like NLP tasks. So one of the problems with transformers is that they're actually like way slower compared to like CNN based models, but now we can see that we start to get these models here that can run like closer to real time. And also like the transformer models, if you're fine-tuning them on your own custom data set, they are actually like slower to converge compared to like the YOLO models, which is based on a convolutional neural network. But again, like the development and improvement of these like transformer based models and actually like the development going on for running these models in real time, there's a lot going on, so it will be able to run in real time, and the performance is also very good compared to the YOLO models as well. So if you don't really care about like real-time detections either, or if you want to run on the CPU, you just want to get the best accuracy possible, you should be able to run it with this model here and get some really nice results. You can try to compare with the YOLO models. We might do that here on the channel in the future, so definitely hit the subscribe button under the video, and also the bell notification so you get a notification when I upload those videos. So right now we actually like have a lot of different kind of like object detection model out there. We have a lot of YOLO models, YOLO 5, 6, 7, 8, and now also YOLO NAS model. We also have these transformer based models here, VIT models for object detection. They are also really good, and they're starting to become faster and actually like run in real time, as you saw in this video here. So it's actually like pretty nice. There's a lot of models out there for object detection. I'm definitely going to create some videos here on the channel comparing some of the models, both the YOLO models, but also now when we have the YOLO models, so the CNN models, and also the transformer based models. So we're going to do comparisons between those two, and that is actually like a really interesting comparison that we're going to do. So thank you guys for watching this video here, and I just hope to see you in one of the other videos. Bye for now.